So friends, we are going to study a linear control system and the stability analysis of the control system. Okay, at the beginning, let me define what is a stability. Stability. So, stability, if a system is there and a certain input is given to the system, and if the output of the system develops oscillations, the oscillation can be constant oscillation, or the oscillation can be the increasing one, and the oscillation could be a damped one. So this is the steady state. So here if we see, then the sustained oscillation is there and the system is unstable. However, it is marginally unstable, not completely unstable. Marginally, we can say at the verge of instability, the system might go. However, here we see that it is going, the oscillations are going on increasing. So this is absolutely unstable system. Whereas in this one, this is a damped system. Here the oscillations are at the steady state. As we are reaching, the oscillations are going to get reduced, and such a system is said to be stable. So I think you got the idea of stability. So if a system is a damped system, then system is said to be stable. If the oscillations are sustained type, then the system is said to be marginally stable. However, if the damping oscillations are going on increasing, then the system is said to be unstable. So there are various criteria for studying the stability of a system. Basically, we are going to see absolute stability, and second one is relative. Now absolute one, this is actually, absolute is actually qualitative, whereas this one, relative stability, is a quantitative. So this is a quantitative, or relation, this is a comparative one. Now first we are going to see Routh Hurwitz criteria of stability. There are many stability criteria that we are going to see, but at the beginning, say when you talk about absolute, and this is relative. So in absolute you got two, that is one is your Routh locus, and second is your Routh Hurwitz. Whereas relative, basically this is based on frequency domain analysis. Okay, so here we are going to study this lecture video basically is focusing on your Routh Hurwitz. Okay, so this is a pretty easy method for studying the stability of a system or determining the stability of a system with the help of point to be noted characteristic equation of closed loop transfer function. And how you're getting the closed loop transfer function is 1 plus g s h s, where gs is the forward gain of OLTF, and HS is feedback gain. So this is pretty clear to you people. Now characteristic equation, let me just directly jump to the methodology. Now Routh Hurwitz is actually, let me first discuss a bit of Hurwitz. These two people were actually scientists, or you can say a scientist. So Hurwitz, for Hurwitz, if a polynomial equation is given by a naught s to the power n plus a1 s to the power n minus 1 plus a2 s to the power n minus 2 plus so on, then we have got a determinant d1 is equal to a1 greater than 0, determinant d2 is equal to a1 a3 odd numbers, and a0 a2, that is e1, that must be greater than 0, and so on. So for evaluating Hurwitz determinants mentioned above, a lot of time is involved. However, in relation to evaluation of Hurwitz determinant, Routh has simplified the procedure for ascertaining the number of positive real part roots of a polynomial, and the method is called as Routh Hurwitz criteria. Okay, so let us jump to Routh Hurwitz criteria. So Routh Hurwitz criteria. And this is a pretty simple method, however certain point has to be taken care, and this I would explain with the help of examples. Now first example I am taking is, okay, let me change the pen. So apply the Routh criteria to determine the stability of the system, having the characteristic equation as given. So characteristic equation is equal to s cube plus s cube plus 4 into 100 s square plus 5 into 10 power 4 s plus 2 into 10 power 6 is equal to 0. This is a question I have taken from the book by Professor B.S. Man K. Okay, so let us solve it. So this is the characteristic equation. Okay, this is the characteristic equation, and Routh table if we make. Okay, so Routh table we are making, so s cube and s square, s1 and s0. So from there you can see this is 1, this is 5. Okay, this we can simplify as 10 square to be common, so this can be p cube plus 4p square plus 5p plus 2 is equal to 0. Okay, so this is 1 5, this is 4, this is 2, 4 5 is 20, 4 into 5 minus 2 divided by 4, 4 we get 4.5, and here we get 0 0, and this is 2. So we see in the first row all the coefficients, these are positive, hence there is no sign change also, so the system is stable. So don't go on this. This is actually, this you can consider to be the characteristic equation, and just you can see from the Routh table that how the stability is determined. Since there is no root change in the first column, this first column, so the system is said to be stable. Now let us take one more example. Example 2. Now in this case the characteristic equation is given by s to the power 5 plus 1.5 s4 plus 2s cube plus 4s square plus 5s plus 10 is equal to 0. So this is our characteristic equation, and forming the Routh table, Routh Hurwitz table, so we get s to the power 5, s to the power 4, s cube, s2, s1 and s0. Now here you can see from the equation that this is 1, this is 2, this is 5. I hope you are able to get this. For say s5, here s5, then choose the odd one 2, and then the next odd one, this is 5. Now for s to the power 4, you gonna choose 1.5, this is 1.5, then you choose the next even number, this is 4, and this is of course 10. Now again cross multiply and subtract 15 to 3, and this here getting minus 0.66, and here getting minus 1.66, the here you're getting 0. Again if you solve, then here you're getting 0.227, and here you're getting 10, 0, 27.4, 0, 0, here you're getting 10, here you're getting 0, here you're getting 0. Here you're getting this minus this divided by this, so it's like 1 into 4 minus 1.5 into 2 minus 4 into 1 divided by 1.5. So 3 minus 4 divided by 1.5 is equal to minus 0.66. Okay, so this is how you are getting. So here you can see this is negative, so from here to here there is a one sign change. Similarly, again from negative to positive, there is one another sign change. So in total we have got two sign changes. And what does that mean? Number of sign change means number of roots on right hand plane. What plane? S plane. I think you know about the S plane. S plane is just this one. This is real axis and this is your j omega axis. So this is your S plane. So here if the roots are on this side, the system is unstable, and since we have two roots, so the system is unstable in this case. Okay, so here you understood very well. Now let me take another example. These examples actually I am taking to make you understand the points that has to be kept in mind while dealing with the Routh Hurwitz criteria. Now next character equation is s to the power 5 plus s to the power 4 plus 2s cube plus 2s square plus 11s plus 10 is equal to 0. Okay, so this is your equation. Now again doing the same procedure around table, s power 4, s power 3, 2, sorry this is 2, then this is 1 and this is 0. So for 5 we have 1, then next is your 2, next is your 11. Again for s power 4 we have 1, then is 2 and then is 10. Now 1 into 2 minus 2, here we will get 0. For this if you solve 11 minus 10 divided by 1, that is you get 1 and this one 0. So what we see here, that element in the first column, element in first column and third row is equal to 0. Now what we have to do here, actually the third element in the first column is 0 and thus the Routh criteria fails at this stage. This difficulty is solved if 0 in the third row of the first column is replaced by a symbol epsilon and the Routh array is formed again where epsilon tends to be 0. Okay, so just keep this in mind. Now sign change, again we have to look at the sign change. Okay, so this I am replacing by epsilon and then again solving it. So epsilon into 2 minus 1 divided by epsilon. So for a second, okay, just a minute. Delete this one. Okay, so this I am tending to epsilon and so I get here 2 epsilon minus 1 upon epsilon, and this I get 10, this I get 0, again this one I get 1 minus 10 epsilon square upon 2 epsilon minus 1. Now how to get that if there is a sign change? So for that we do limit 2 epsilon minus 1 upon epsilon, for epsilon as I have mentioned tending to 0. So if you solve this one, you get 2 minus 1 upon epsilon, this is equal to 2 minus infinity is equal to minus infinity, so negative. And second one, limit 1 minus 10 epsilon square upon 2 epsilon minus 1, epsilon tends to 0. On solving this you get 1 minus this epsilon, 10 epsilon by 2 minus epsilon square by 2, and this is 1 minus this is 0, this is 0, so you get 1. So the two limits we have got. So total sign change, if you see, 1 epsilon, then minus infinity, then 1, and then 10, and here you get 10 0 0. So again from here to here and here to here sign change, and here also sign change. So total number of 2 sign changes, that means 2 roots on right hand plane as plane. We have 2 roots on the right hand, so again system is unstable. Okay, so now let us look at the another very beautiful example. This is example number 4, I hope. Yeah, again characteristic equation. If I write, then it is s to the power 6 plus s5 plus 5s to the power 4 plus 3s cube plus 2s square minus 4s minus 8 is equal to 0. Now Routh table, s power 6, s to the power 5, s to the power 4, s to the power 3, s to the power 2, 1, and s to the power 0. Okay, here you get 1, 5, 2, minus 8, and here you get 1, 3, minus 4, 0. 1, 5, 5 minus 3 by 1, that is you get 2. 1 into 2 minus this is 4, and divided by 1, that is minus 4, you get 6. Then this is minus 8, this is 0. Now 2 3 is 6 minus 6, you get 0. 4 to the 8 minus 8, and you get 0, you get 0, you get 0. So you see, in the previous case only one element was here, all elements of s cube row are 0. So what we have to do, what does that mean? So if all the elements of a row in Routh's tabulation being 0, it indicates a pair of conjugate roots on imaginary axis. and on substitution of the coefficient of dA by ds, this we are going to see in the 0 element row, no sign change is noted in the first column of Routh tabulation, then system is said to be marginally stable. Remember that if all the system, if all the elements of that if all the elements of any of the row is completely zero, it means a pair of conjugate roots are lying on the imaginary axis, and previously I have told if roots on the imaginary axis, then we have sustained oscillation and that means the system is marginally stable. Okay, so this is it. Now how to find auxiliary equation. Auxiliary equation is AUXILLARY auxiliary equation. This is made from the row just above the row which has become totally zero, that is 2s to the power 4 plus 6s square okay minus 8, and this is equal to as. So what is das upon ds? This we get 8s cube plus 12s minus 0. So this would be the next row, it is s cube row, this one previous row. Okay, now how to go about that? So again you have to form the Routh table. Redo it. So we are redoing the Routh table once again, and we see again is 6 s5 s4 s cube s2 s1 and s0, and s6 we have 1, this is 5, this is 2, this is minus 8, this is 1, this is 3 minus 4 0, 5 3 2, this is 2, this is 6 minus 8 0, and this was previously becoming 0. Now we have replaced it by 8, then 12, then 0 and 0. From there this is we are getting from dA upon ds, and this we are getting from auxiliary equation, that is as. Now next is again the same, follow the procedure, that is s2 is 3 minus 8 0 0, and s1 you are getting 100 divided by 3, this you are getting 0 0 0, this you are getting minus 8, this one, and this is you are getting 0 0 and 0. Okay, now look at the first row, how many sign changes? So just here if you see sign change, so there is just one sign change in this case, So 1 root on right hand plane. However, system is marginally stable, and why I have explained, because there are imaginary axis. We have roots on imaginary axis, that is why the system is unstable. So you understood this. Now a bit of more concept I would like to propose here with the help of next example. Example number 5. Now what happens when all the elements of a row in Routh's tabulation being 0 indicates a pair of conjugate root on imaginary axis, and the system is marginally stable if no sign change is noted in the first column of Routh's tabulation. However, in the previous case we have one root on the right hand side, so instead of marginally stable, the system becomes unstable. If there was no sign change, then the system would have been marginally stable. However, since sign change was there, so the system becomes unstable. Now another concept. Let us take one more example. Example 5. Fs is equal to s to the power 6 plus 3s5 plus 6s4 plus 12s cube plus 12s square plus 12s plus 8 equal to 0. This is our characteristic equation, and if you form Routh's table S6, S5, S4, S3, S2, S1, S0, so here you get 1, 6, 12, 8 and 3, 12, 12, 0. On solving this you get 2, 8, 8, 0. Now this one, 2 to the 4, 12 into 2 minus 8, 324 divided by whatever gives 0. This becomes 0. Again 24, 8, 3, 24. This is again 0, 0, 0. Same procedure, we apply auxiliary equation. You get s to the power 4 into 2 plus 8s square plus 8 is equal to 0, and dA by ds you get 8s cube plus 16s plus 0. Okay, so you got the new coefficients. This you are getting 8 and this you are getting 16. Okay, now again solve it. So what you see, again you got 0. It is 64 and 2, it is 16. Okay, still you are getting 0, and here also you are getting 0. I put it double star. Again you form an auxiliary equation here. So what you get, 8s cube plus 16s. This is your A2, and dA2 by ds you get 24s square plus 16. Oh, sorry, this one is s square. Okay, sorry, here this is 2 and this is 16, so this we are getting auxiliary equation 2, we are getting 4. Auxiliary equation we are getting to be 4s square plus 8. This was 864 minus 16 to 32 divided by 8. Okay, just a minute. So here we are getting 4 and here we are getting 8. Sorry, mistake. Now here if we solve, and 64, 8 is 64, here we get 0. Okay, sorry for the mistake, and again here we get 0. So this would be the auxiliary equation, and it would be not this, it would be, this would be A2 is equal to 4 s square plus 8, and dA2 by ds that would be 8. So the equation I get is, here I get, this is 8 and this is 0, and so from here you get this one is 8. Now observe the first row. So in first row, here and here you got 2 times the complete row equal to 0, and what does that imply? And however, there is no sign change. Sign change is not there, but we have got the complete row to be 0 2 times. And what does that mean? There is no sign change in the first column. The system is stable. However, so first thing, no sign change. So what does we infer? System to be stable. Okay, just keep this in mind. Second, but if complete row is equal to 0, then what? Marginally stable. Again, but if 2 rows are 0, that is, this implies that pair of conjugate roots on imaginary axis are in multiple order of conjugate roots, and thus there is no change in sign in the first column of Routh tabulation, but existence of 2 rows having 0 element makes the system. So from these 3 points we infer that system was unstable. So this is quite a classic example. So on the first hand, the system could have been marginally stable since there was no sign change in the first column. However, what you see, there was complete zero row, two times, once here and the next time here. What does that mean? It means the existence of two rows having zero element. It means that pair of conjugate roots on imaginary axis are there with multiple order, that is, here the order was 2, and this made the system unstable. So these are the classic examples. If you see, and you would make no mistake in understanding the concept. Now let us just solve few more example. Example number 6, I think. Okay, now system is given GS, forward gain, e to the power minus st upon s plus 2. Now what it has asked: using the Routh criteria, investigate the stability of a unity feedback, that is h is equal to 1, system whose open loop transfer function is given by this equation. So 1 plus gh equal to 0. This gives the characteristic equation to be s square plus 2s plus e to the power minus st is equal to 0. So from the Routh tabulation, this is s square, s1, s0. This is 1 is e to the power minus st, this is 2, and this is 0. And solving, you get, now this, what to do about this? Expand it. It's not as tough as it looks. Expand it. 1 minus st minus s square t square by 2 factorial, and so on. Now taking just two terms, taking two terms only, what we get? E to the power minus st is equal to 1 minus st, and just put it here on the table. So this is, but just take the first term, not this one also. So this is 1, this is, okay, let me just rewrite the equation. S square plus 2s plus 1 minus st, taking the two terms here, this is equal to 0. So we have s square plus 2 minus ts plus 1. Now this is the new characteristic equation from Routh Hurwitz with the help of that one. So here get 1, and this is also 1, and here you get 2 minus t, and this is 0. So solving, you get here 1, and this is 0. So what you see, sign change you have to see. Now for marginally, the condition for the stability of the system, all the roots on the first, coefficient on the first row must be 0. So 2 minus t must be greater than 0. This implies t must be less than 2. This is your answer. Okay, now next example, a quick example, very small one. Okay, here a bit of relative stability. I'm not going on detail, but just with the help of Routh, just a bit. This is question sometime asked in GATE exams. So the question is, determine the value of k such that roots of characteristic equation given below lie to the left of line s is equal to -1. So this is a kind of relation to determine the value of k, and the equation gh1 plus gh characteristic equation is given directly s cube plus 10s square plus 18s plus k is equal to 0. Okay, now what we have to do here is relatively they have given, so s1 is equal to s minus 1, because to the left of line s is equal to -1, we have to check if the roots of the character equation given here lies to the left of that one. Okay, so Routh tabulation. S cube s square, this is s1, this is s0, this is 1, this is 1, this is okay. Let me solve it by putting s1 minus 1 cube plus 10 s1 minus 1 square plus 18 minus 1 plus k is equal to 0. So on solving you get s1 cube plus 7 s1 square plus s1 plus k minus 9 is equal to 0. Okay, so this you are getting is 7, this you get is k minus 9. 7 minus 1 minus k minus 9 divided by 7, that is 7 minus k minus 9 divided by 7. This you are getting 0, here we get k minus 9. Now for stability, all coefficients of first column must be positive. This implies 7 minus k minus 9 divided by 7 must be greater than 0, and secondly k minus 9 must be greater than 0. So from here you get k must be less than 16, and here you get k must be greater than 9. So k lies between 16 and 9. So for this value of k, the roots would lie on left of s is equal to -1, or with the plot if I explain, this is your -1, the roots would lie this side, this would be the roots, that is lies between 9 and 16, hence we got it. So this is all about in Routh. Next time we will see few more stability criteria like we will see in the next video. We will see about root locus method and its beauty of the root locus, and other like Nyquist, pole zero plot. Then you have Nyquist plot, then very other like board plot, then Nicole chart. So these all other methods of understanding the stability. So this we are going to do like board plot, then Nyquist, then pole zero, and then Nicole's chart. So this we are going to deal in next video. Thank you.